Hello and welcome to, I guess this is volume or episode 6. And this is our casualty list. Oops. I'm sorry, buddy. It's always sad when one of you passes. But what are you going to do? Anyway, that's everything that came out. I used up the last of my X and Y capacitors on this set and ordered some today. They're supposed to be here tomorrow, so we can get on with the next one. We're going to finish up today with the Trav-Ler, Travler. Get my buddy. Should I put him in a shoebox and put him out back with my hamster in the backyard? No, I probably won't do that. We'll get rid of this stuff. The capacitors will go in my to-be restuffed box. I'm just going to drop them over here for now, get them off the bench. Something I keep meaning to touch on and I keep forgetting is to tell everybody where I'm getting schematics. Now, the guys who do this a lot, they know probably where to get everything. But for those of you who are just starting out, I start by going to the radiomuseum.org. And the radiomuseum.org will have a page. It'll tell you what year the radio was born. And tell you where it was made, what country, who the manufacturer was. But more importantly, they will have circuit diagram reference, and it will say Riders Perpetual Volume number 15. So you jot that down. Now you can go right on the radiomuseum.org website and download a schematic from there. They'll let you, if you're not a member, they'll let you do one a day. And I'm throwing them some a donation, by the way, because it costs money to archive all of this stuff. But the schematic you get from them, do I have it here? Oh yes, I do. I have it here. Typically looks like this. It's just the schematic and no alignment information. Now this is enough for the guys who do this all the time. But they can be kind of hard to read because they're shrunk down, and even though this is a blown up one, this is directly from Riders. And I'm going to tell you how to get the Riders. You go to nucow.com. That's nucow.com. And from your reference from the Radio Museum, you find volume 15, and then download volume 15 and scan through it, and you'll find your radio in there. Now, each volume, I think they cover volume 1's number 1 through 23, and I think it dates back almost to 1918. There's probably a couple hundred schematics in each volume, so it can take some time to find your unit, but they're all in alphabetical order. Using the slide bar on the side of your computer is tough because they fly by so quick that you'll pass them several times before you zero in, but they're all there. They're the full Riders manual. And I searched their website several times trying to find a place to make a donation to them, because it must have taken somebody... Okay, I did plug the power supply into the camera, but the plug wasn't in the wall. Now I want somebody to explain to me how the power can make it 50 miles from public service to my house and not jump that last 6 inches. Always been confused by that. At any rate, I tried to find a place on nucow.com where I could make a donation. It must have taken a guy weeks, literally weeks, to scan every page of all those Riders in, and they also have the index. They have all the indexes at the beginning. But unless you know what year your radio was made, it can take hours to go through all the indexes until you find your radio. So I always jump over here to radiomuseum.com, or excuse me, .org, radiomuseum.org, get the rider's volume that it's in, and it'll tell you right on the second page of this. Rider's perpetual volume number 15, then I'll open volume 15 and download my schematic. You can also go on eBay, and a lot of times they'll have the SAMs available. On a simple set like this, I usually have enough information from one source. But if you're working on something that has AM and FM and perhaps several shortwave bands on it, you'll probably want to have both the riders and the SAMs, because between the two of them, one of them will have information, the other one doesn't, and vice versa. And between the two of them, you get a lot cleaner picture or clearer picture of what you're working on. So that's where my information comes from. Now, several videos back, I was saying how the IF alignment isn't real critical as long as both transformers are tuned to the same frequency. You can tweak the local oscillator to shift your IF to wherever these are tuned to. Now this only pertains to these simple radios. I know someone's going to come out of the woodwork. If you're working on a dual conversion radio or a shortwave radio, you know, something like a nice old Hallicrafters, you're going to want to get your IFs spot on. But on these guys, to be honest, you can tune them by ear most of the time, after you've got your local oscillator correctly set. And I showed you how to do that without a single signal generator. You could do it with a receiver. As long as you got a digital readout, you set your local oscillator where it belongs and then tune your IFs by ear. I had promised to do that to a radio, to jack it up so that the IF wasn't aligned correctly, and prove that the radio would work just fine. And you remember when we powered this up, it worked just fine. You know, I can tune all the stations in that are around here, and the radio works just fine. So I wasn't going to bother too much, you know, being too specific with an alignment on this set. This set, by the way, tells you to do the alignment a little differently. Most documentation will tell you to connect to the grid of the IF amplifier tube and adjust your second IF, and then move to the grid of either your converter or your RF amplifier and adjust your first IF transformer, and then go back and forth and tweak them for the best performance while lowering the signal level. This radio, the documentation doesn't tell you that. It tells you to go directly to the tuning capacitor. It says set the tuning capacitor at minimum, connect at this point right here, which is the grid of the RF amplifier, and tune the IF transformers. So I went to do that, and I don't have to jack a radio up for you. This one's thoroughly jacked up, and yet it's still working. I am going to connect my signal generator, which is presently on 455 kilohertz. Yeah, you can see the signal generator. Right. So I'm going to go down here and connect to, and this is still on my isolation transformer. Where the heck do I want to go here? I don't want to get into anything live. Here we go. There's ground. That's a safe point. And I'm going to go up here. It tells you to go to minimum capacitance and put your signal generator right on the tuning capacitor. I don't hear anything from my signal generator. Now watch. It isn't until I get down to 400 kilohertz that I find the IF on this. That's that's 150 kilohertz, 155 kilohertz off of alignment. Is that right? No, 55. I'm sorry, 55 kilohertz. One day I'll learn how to do math. That's 55 kilohertz away from where it belongs. Not 5 kilohertz, not 10 kilohertz, 55 kilohertz. That radio is misaligned, or the IF is misaligned by. Somebody went in there and tightened all the loose screws. And I've had them come in the shop like that. I tightened these screws and now the radio doesn't work. But obviously, you can see the radio is working just fine. And most of the stations are pretty close to where they belong. Another thing I found is the oscillator pattern down here is cranked all the way in as far as it'll go to make the radio work, to get them up into the band. But the radio functions. It's perfectly usable the way it is. So that's why most of the documentation will tell you to go to the IF amplifier, grid of the IF amplifier, tune your second one, because you won't have 2 stages of filtering, you'll only have 1 to deliver. So peak that one up, then move up here and peak this one up, then you can go back and forth and dial them in. So let me get this thing turned over and we'll do that. We have our signal generator connected to our IF amplifier. Pin number 4, the grid that's going to amplify our 455 and feed it to the primary of T2. And we have to tune T2 on both sides until we get our signal through our IF amplifier. Now, something I didn't mention earlier on, I did mention this years ago when I did this with the transistor radio. There's more going on here than 455 kilohertz. Our converter is non-discriminatory. It doesn't care who it amplifies and passes on. Remember early on in this series I said that this coil of wire and this capacitor form a resonant circuit, and it's our first filter. It's so that when we tune for 1600, that's going to be the strongest signal coming through either our RF amplifier or being fed into the converter. It kind of pre-selects the signal that this tube is going to see. So let's say our station that we want to listen to is at 1600 kilohertz. And as we talked about earlier, our local oscillator is running at 2.055 kilohertz, okay, 2055. You subtract this and you get 455 kilohertz, which is our intermediate frequency. That's what this amplifier is designed to tune. It's basically a filter, because coming out of this tube as well is the sum of these 2 frequencies, which is 3655. We don't want 3655, we don't want 1600, we don't want 2055 coming through. All we want coming through is the 455. But if you were to look at the output of this tube with a spectrum analyzer, you'd see all 4 of these frequencies, and if there's leakage coming in, there'll be a bunch of others coming in as well. We only want that 455 kilohertz frequency to come down the chain and be amplified so that we can detect it here. And we're going to talk about this in a minute. So this is basically another filter. You'll hear them called IF filters or IF transformers. They're intermediate frequency filters. Their real job is to filter out all these other signals and only give us the 455. That's kind of an important concept to understand. So now that we're on the tube, the speakers or the volume is wide open. We can see the radio's receiving, but we're not hearing anything of our 455 IF frequency that's supposed to be coming through. If I can figure, oh, there's my screwdriver. And did I mention it yet? I have already checked the trimmer caps with a voltmeter so that I know the trimmer caps in here are cold. They are not live or hot. And that's important. You wouldn't want to use a regular screwdriver if they were hot. So let's see what we can find with we should be, I'm on minimum capacitance. Oh, there we go. This thing was so far off. There wasn't anything getting through it. Which means it's doing its job. It's filtering out frequencies that it's not resonant at. I'm going to lower the level. Lower it some more. You want to do this with the minimum signal possible. And I'll explain why in a minute. We're going to explain the detection and AVC circuit. Okay, so that transformer is pretty close. Now I'm going to move to the front end of the radio where they tell us to do our alignment in this particular set. They tell us to go up right up here. And now with the second IF tuned fairly close, we should be able to find a peak on our first. And there it is. And you can tell it's a whole lot louder. And a whole lot louder still. And you can tell from the noise leaking through, I'm not injecting a very strong signal. Now you might be asking yourself, how would you do this if you were doing it with the waterfall method? You saw in that waterfall there's a fairly wide spectrum available. That 55 kilohertz would readily be available. Instead of being on the center of the screen where we want our 455, you would see that spike show up off to the side. Then, with the radio working and playing with your local oscillator set correctly, you would just start slowly tweaking the IF transformers and watch which way that spike moved. You don't want to move them a lot because you'll get lost. You don't want to lose your signal entirely, but turn them so that it gets a little weaker and moves in the correct direction. Then tweak them a little bit, moving in the correct direction, and pretty soon you'll be able to move that IF frequency spike that's on the waterfall display that you saw earlier when I did it without a signal generator. You'll be able to move that spike, that IF spike, over to where it belongs. That'll work just fine. You don't need a signal generator and you don't need an oscilloscope. But if the radio is working, you can just find out where that IF spike is showing up on your screen and slowly tweak it without losing the signal, because if you lose it you can get lost. It'll move over, retweak, and you just keep doing that until it's where it belongs. Alright, ba-dum-bum-bum. Oh, yes, I was going to explain why it's important to have a very, very weak signal when you're doing this. What I'm going to show you now is a very simplified circuit or simplified section. We're going to get rid of a lot of the clutter that's on here of our first detector and our AVC line. This orange line is our AVC line, and I've mentioned before our AVC line or AGC line, whatever you wish to call it, which controls the gain of the front end of the radio so that it doesn't rise and fall very much when the signal fluctuates, and it doesn't overdrive everything. It keeps it within a fairly constant gain level. That comes out of our detector along with our audio. Coming out of our detector, I've got little blue dashes here. They go through the volume control, into our first audio. They go back into the same tube. They come out of the detector portion and then back into the grid of the triode. That tube, I think I've got one. Let me move this just a minute. Yes, I do. It's usually pretty easy to spot, unless they're metal tubes, your detector and first audio. Let me get in close here. You can see, are we in focus? I hope so. The top section is just a small triode audio amplifier, and the bottom section, you can see it's separated. We have our detectors. They're nothing but diode rectifiers. That's all this is. When they say detector, they mean diode rectifier. Okay. So our RF signal, our IF signal. Well, first of all, let me show you this little clip. Okay, I hope this helps to make it a little bit clearer. I've manipulated things a little bit and use a digital oscilloscope here to do some captures, waveform captures. This is our carrier frequency of 455 kilohertz. Now remember, our real carrier came in at anything from 550 to 1700 kilohertz, but it gets converted down to 455 kilohertz intermediate frequency, which becomes our carrier, if you will, because it's just the signal converted down to 455 kilohertz. Now I'm going to add in AM modulation. Now that we have our AM modulation added in, we can still see our carrier frequency in here, or our IF 455 kilohertz. And this envelope here is our 400 hertz audio. Now this could be voice, music, whatever. In this case it just happens to be a steady tone to make it clear on the scope of 400 hertz. My 400 hertz tone, and you notice it's both positive and negative about the zero line. That's the way amplitude modulation works. It merely changes the amplitude of the carrier up and down in step with the audio frequency. Then we need to take and run it through our detector. When we run it through our detector, effectively what we're going to do is this. We end up with this envelope. We end up with pulses of our 455 kilohertz, and these pulses vary in amplitude at the audio rate, at the audio frequency. Now I'll take you to how that's filtered out, converted into AVC voltage and audio to pass on to the speaker. Okay, now that you've seen your RF and your IF envelope, what these two detector plates are doing in our detector tube is they're taking that full AC signal and they're trimming off the top half of it. They're cutting it completely off, and what you end up with is your RF negative going pulses, and it's a pulsing signal, but it forms an audio envelope like this. Okay, that's coming out of here, off the detector, and at this point right here we have a signal that looks like this. Then it comes down here to this 100 picofarad, 0.0001. Sometimes you'll see it called microfarads. They mean picofarads. 0.0001 microfarads, or they'll say 100 microfarads. They mean 100 picofarads. One other thing of note, and this is important, on a lot of these schematics you'll see M in front of a resistor. Look your schematic over, and there may be a note on there that says M equals 1000. Okay, it may equal 1000. So look for that. Especially if you have resistors marked 1 meg, 2 meg, and then 3M. If it said 3M on this, 3M, that means it's 3K, 3,000 ohms. It's an old way of notation, and it was changed, I think, sometime in the 70s. They finally started saying, you know, that's confusing, it doesn't make any sense. But this is the way they did it way back in the day. M meant 1,000. They would spell out 1 meg, and then they would say 3M for 3,000 ohms. And somebody said, hey, doesn't 1M make more sense for 1 meg ohm and 1K for, I thought, well, K for 1,000? I don't know where they got the K, but anyway. Be aware that M doesn't always mean meg ohms. Okay, where were we? We have our 12SQ7, which is our detector and first audio amplifier. We have this envelope here coming into this rectifier section, and it's getting rectified into this. This 100 picofarads is a filter of sorts. Think of it as a filter. It's short-circuiting the RF portion of the signal so that it ends up looking just like a varying minus voltage, a DC voltage that varies, minus DC voltage that varies at the audio rate, in this case 400 hertz, like I showed you in the previous clip. So we filter out most of the RF here, goes into our volume control through this little coupling capacitor to keep any DC that's here off. All we want is the varying AC now, so it'll go from a negative DC. The capacitor will change that into just a regular AC signal because it won't pass the DC component, but it will change. It will pass it through as a varying DC varying voltage. That goes to the grid. That gets amplified. Our B plus supply here supplying this anode, and this is the capacitor I'm always harping on that has to be changed before you power these up, because this B plus voltage will leak into the grid of this tube and drive this tube into conduction way past where it should be operating at. That's our audio output tube. So that's that critical capacitor I'm always harping on. And I wish I'd put this down, but if you understand how the capacitor works, it will pass the AC component. It will make it look like it's got a line here. It'll pass the AC component and filter out the DC so that it doesn't affect the bias on this tube. Then we have a 2 meg ohm resistor and a 0.05, and then a 1 meg ohm resistor and a 0.05. You can almost think of this as a pi filter. In fact, you could think of the whole thing almost as a pi L filter, because this looks like the letter pi and this is an upside down L. The purpose of this is to allow this capacitor to convert this varying AC voltage, or varying audio voltage, which we want to pass on to the tube so we have audio. But we don't want this voltage affecting the control grid of our IF amplifier or the converter or RF amp. Now, some radios won't have an RF amplifier. This will go directly to the control grid on the converter to control its gain. On this particular radio we're working on today, it goes to the first tube, which is an RF amplifier, and it bypasses the converter. The converter doesn't have a level control tied to it. But what's important is you understand this portion of the circuit. This is basically a filter, just like you've seen in the power supply. We come out of the tube, we go to a capacitor, we go to a resistor, we go to another capacitor, and then our clean DC voltage comes out. It's to filter out the ripple created by our rectifier. So this is filtering out this ripple, which is undesirable, because if the tubes are going up and down, they're going to feed back to the detector. The detector is going to try to feed back that voltage, and you're going to end up with all kinds of oscillation. If these capacitors are open, or this capacitor is open, you can get a condition that's called motorboating. It sounds like an old-fashioned one-cylinder engine on a fishing boat going pop 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 pop, or it'll just squeal like crazy. That could very well be these two capacitors or this capacitor. One or all of them could be open. That will allow feedback into the control grid of our converter or RF amp or our IF amp. So if you got squealing or motorboating, these are your suspects right here. Usually you can go after these, change these capacitors, and that problem will go away. Very, very common. That used to be something that was in all of the textbooks years ago. Motorboating, because way back when these radios were built, those capacitors often failed in 10 years, and these sets would motorboat and squeal and howl. There used to be thousands of radio repair shops when I was a kid. They're gone now because nobody works on this stuff anymore. Everybody's a parts pusher. So bear that in mind. This is nothing but a rectifier changing this signal, or the full envelope rather, you saw in the video, to this signal. Then this is a filter to remove the RF component or IF component, so that you end up with this varying DC voltage, which is fed into your volume control. This makes it appear to be just an AC signal that tickles the grid of this tube. It gets amplified and fed onto the audio output tube. And this is a filter. This is nothing but a filter circuit to convert this varying DC voltage to an average steady voltage. And the stronger the signal coming in, the bigger the signal coming in, the more this will go negative, and the more it will reduce the gain of the front end of the receiver. I hope I'm not being too repetitive here. I know somebody left a comment last week. I sped his video up to 1.5 times and it sounded more normal. And I keep telling people, I'm trying to teach people so they understand these circuits. So I'm going to take it slow and methodical. And actually, I found the comment kind of funny. To be honest, I got a kick out of it. Means I'm doing my job. All right, so we're going to convert this varying DC signal to something that's more averaged out, so that when it gets to the grid of our IF amplifier and our either converter or RF amplifier, it has a negative voltage that's fairly steady. The stronger the signal, the more negative it'll go. It'll bring the gain of the tubes down. As the signal gets weak from fading and there's less voltage coming out, less negative voltage, the tubes will start to conduct more gain to level the signal out. It really is that simple. Nothing but a rectifier and a filter. That's all you've got here. Okay, hope that makes sense. Okay. And off camera, not to bore you to death, I just went ahead and did the RF alignment. And I've mentioned it several times with these sets, when there's only one adjustment, you kind of have to balance the 2 points. It tells you to set it up on the high end, and it says the low end will be correct. It's never true on these real simple sets. This station is 610. Should actually be up here, but it's pretty close. And then up the other end we have 1370. See if I can get it to come in. Right there is 1370, so it's a little bit down on this side, and it's a little bit down on this side. This, of course, being 1400 in between these two major ticks. So 610's a little low, 1370 is a little bit high. It averages out. It's close enough for this type of radio. And very shortly, I hope that the little window will be in. This is how our case turned out, if you remember how that thing looked in the beginning. I've still got a few speckles here and there, and I've got to polish it. This is just what it looked like after I got the paint off it. Nothing else has been done really to it at all. Just wiped it down with some lacquer thinner after I got the paint on it, and wiped it with a rag. And there's still little speckles of white here and there that I missed. There's some stuff down in here I'll have to get out with a dental pick over time. But all in all, this is going to be a nice little set when it's all cleaned up. It's a fairly nice little receiver. That's the end of that one. Now coming up in the next couple of, well, not the next couple of episodes, the next 2 sets that we do over the next however many episodes it ends up being, we'll try to keep them shorter. The Triad radio and the General Electric dual band AM shortwave radio, both of them have some very unique features that I don't think most of you have ever seen. The power supplies in them are downright weird, and you'll understand that when we get to it. But the first one we'll jump into is the Triad, the one we don't have any schematics for. That'll be teaching you how to understand what's in that set, even though we don't have a schematic. We really don't need a schematic. It's going to be the same type of receiver as this. It's a 6-tube set, got an RF amplifier in the front, and I'm not sure what the tube lineup is. I'm sure it's very similar, but just because we don't have a schematic for it, we can build on the knowledge from this one, because we know we're going to have an RF amp, a converter, an IF, first detector, and an output tube. And even if the tubes aren't the same, we can use our tube manual. You do have a tube manual, don't you? And we can look at the pinout of whatever tubes are in that set, and we'll be able to do the same diagnostic tests, the same alignment tests, because it's going to use the same technique for the transformers. It's going to be the same idea for the detector first amplifier, IF. Everything's going to be basically the same. It just may have different tube numbers and some different component values. So we should have no problems going through that set, but what is very, very different on that set is the power supply section. And I don't think, like I say, I don't think most of you have ever seen that power supply. Oh, and I was talking about this while this is in my hand. Remember I said this was just like the filter in our power supply. Here's our 2 capacitors with our resistor in the middle, 2.2K, and our 2 electrolytic filters. Well, here's a 1 meg and 2.05s. These work a lot better at audio frequencies and RF. These very high value capacitors are for filtering out 60 hertz, but it's the same thing. It's a pi filter and a pi filter. After a while, you start noticing these things and realize that it's just a series of filters and tuned circuits that make these things work. They're pretty basic. Okay, I'm the radio mechanic. Gonna wrap it up. Don't want people having to turn up to 1.5 times speed just to get through. We'll catch you very soon with some unique radios, so please come back. See ya.